I think we should get started to make sure we give our speaker enough time. So today it is my great pleasure to welcome Cora Fujiwara, who will be she's our third speaker in this new series, Science by Diverse Scientists. So Cora actually grew up in Southern California, like I know many of our CalBridge scholars did. She then got her bachelor's in physics from UC Berkeley before going down to UC Santa Barbara to get her PhD in physics. And she's currently a postdoc at the Center for Quantum Information and Quantum Control at the University of Toronto. And she'll be telling us about how to get ultra cold today. She'll be telling about her work on cold atoms. So Cora, if you want to share your screen and take it away, welcome.
Yeah, thank you so much, Alex, for that very nice introduction. And thank you, everyone, for having me here to speak at this CalBridge seminar. I'm very excited to share with you some of the work that I've been working on the past few years. Indeed, making atoms not only cold, but ultra cold. So hopefully everyone can see my screen now. And yeah, so as Alex mentioned, I'm currently based at the University of Toronto, so here on the East Coast. But most of the work that I'll be presenting today is work that I conducted during my PhD at the University of California, Santa Barbara. And yes, so today I'm going to tell you all the really neat and exciting ways that you can use light, namely lasers, to cool and trap atomic gases. And we're going to use them for a purpose, what I'll define later, called quantum simulation. And we're going to use that to study a variety of really novel transport phenomena. And so what I'm actually showing you on this title slide are two images of ultra-cold atoms. So on the left-hand side is a gas of atoms being cooled down to around like 50 nanokelvin, which forms what's called a Bose-Einstein condensate. And on the right-hand side is an image of fermionic potassium living inside an optical lattice. This is a periodic potential made of light. And what you're seeing here on these little, each of these little lights over here actually corresponds to a single atom trapped in one of these lattices. And we're going to talk about both these things. And so roughly speaking, this will be our plan for this talk. So this being a seminar, I think everyone comes from a wide variety of backgrounds. So I'm going to try to keep this talk as accessible as possible. So unfortunately, that means I won't be able to go into a lot of technical details about how a lot of this work works. But I hope to give everyone sort of a general idea of the flavor of what it's like to work with ultra-cold atoms. Okay, and so roughly speaking, in this talk, I'm going to move my little screen share thing for myself. I'm first going to talk to you about how we can cool and trap gases with lasers. And then what I'll talk to you about when you cool these atoms down, they form what are called quantum degenerate gases. And this will be this Bose-Einstein condensate and this degenerate Fermi gas. And finally, I'll talk about a variety of experiments where you can put those atoms inside periodic potentials made of light. These are these optical lattices. And what I'll show you and discuss is how you can use these for something called quantum simulation. And what we'll do is we'll use this tool to understand transport phenomena in these sorts of lattice systems. And finally, I'll conclude with a couple of comments about my personal journey in academia. And that will sort of conclude this talk. And I hope by the end of this conversation, I hope I've convinced you that indeed studying ultra-cold atomic physics is super duper amazing. Everyone should change fields and study cold atoms. So I hope we all have a lot of fun. So because this is, I think, a seminar, feel free to ask questions and we'll go ahead and take it away. So when I'm talking about, I work in the field of physics called atomic physics, and let's go ahead and start from the very beginning. So here's a one-slide history of atomic physics. So as you're probably aware, the concept of atoms is really old, right? It dates back to the Greeks. And there was this concept that you could say, take matter and divide it down into smaller and smaller constituent parts. And this would, the smallest unit would be this sort of atom. And this dates back to this fellow named Democritus. But it wasn't until, say, the last 100 years or so that it came to be understood that atoms are actually composed of subatomic particles, namely neutrons, electrons, and protons. And this is, really exemplified through this famous Rutherford scattering experiment, where it came to be understood that there was a central nucleus, which is positively charged, surrounded by some negatively charged exterior. And it was with the advent of quantum mechanics that it became understood that these atoms, their energies are quantized, right? And I think this is best demonstrated through this sort of toy model here, which is this Bohr atom, which I'm sure many of you are familiar with. And while it's just a toy model, it has a variety of features which are, I think, qualitatively really important for understanding some of the basic aspects of laser cooling. For example, like this electron is at sort of discrete orbitals, as a cartoon picture. And then when an atom, say, decays down from, say, the n equals 3 shell down to the n equals 2 shell, it'll emit a photon corresponding to that same energy via energy conservation, say. And it turns out that just these ingredients that I'm showing you on this slide are the basic fundamental ingredients that you need to have in order to understand laser cooling. So before I get into that, I just want to clarify about what I mean when I say an atom. So of course, there's all the atoms on the periodic table that we could work with. But for this talk, I'm just going to throw away basically all of the periodic table, and we're just going to be focusing on these group 1 atoms. And the reason being is that these have a single valence electron. So this means that they're basically hydrogen-like. There's a single valence electron orbiting around a positive nucleus. And this, for technical reasons, this makes them particularly amenable to laser cooling. Furthermore, in the experiments that I'll be talking about today, we're just going to be talking about these 3 atoms, namely lithium, potassium, and rubidium. So for reference, these are alkali metals. So at room temperature, they're sort of metals. Rubidium's more of a liquidy-like, but they're shiny. But in this talk, when I'm talking about atoms, I'm not talking about these solids. What we're going to do experimentally is we're going to take these various alkali metals and heat them up. And when we heat them up, they're going to create gases of atoms. And so it's these gases of atoms that I'm actually going to be working with in the lab. And these are the things that are going to be laser cooling. So when I say atoms, you should think about gases of atoms. Okay? So with that being said, let's go ahead and just ask ourselves what happens when an atom interacts with light, okay? So we already talked about sort of this basic idea, right? The spontaneous emission, where an atom goes from an excited state down to a lower state and it emits a photon, okay? So you can sort of think about this in this sort of traditional 2-level system, 2 energy levels, and this photon running array. And for the purposes of this talk, the sort of salient feature about this phenomenon that you need to understand is that just both energy and momentum are conserved. So the atom was once in an excited state, and then by energy conservation, the energy of the photon plus the final energy atom must be conserved. And same thing with the momentum. So in this case, because the photon has some momentum, when the atom emits this photon, it's going to receive a little kick, right? A momentum kick from the photon. So the converse also happens. This is called stimulated absorption, right? This is where an atom is in a lower state and it's going to absorb a photon. And again, both energy and momentum will be conserved, okay? And so these are the basic 2 ingredients that we need to understand to be able to access some basic laser cooling. So to do that, let's go ahead and consider the following thought experiment. So suppose you have some atom, it's moving with some velocity v, and I want to cool it down. That is to say, I want to reduce its velocity. So what I'll do is I'll apply some red detuned laser light. And what I mean by this is that the laser light that I'm applying will have a frequency or energy that is less than the internal energy of the atom that I'm addressing, okay? Which is going to be signified by this detuning parameter, delta. So what will happen is this atom will absorb and then emit photons via spontaneous emission. And the trick here is that spontaneous emission happens in a random direction. So if I average over many absorption and emission cycles, on average, the force from spontaneous emission will go out to 0. And so on average, the expectation value of the force is only going to depend upon the momentum of the light that I'm applying in this direction. So phenomenologically speaking, this force will be equal to the photon momentum multiplied by the rate at which those photons are being scattered. Okay, so we can plug into some equations, and it comes out to this equation for the force here. So this is the photon momentum. And you don't need to know the details of this equation, but I'll just point out a couple of important features, and that it depends upon I here, the local intensity, and gamma here, which is the transition line width, which is basically the uncertainty in the energy of this transition. This parameter lowercase delta here is the total detuning. And in this case, this total detuning will have two components, one which is from the Doppler shift, and the other which is from the detuning in my laser. So if I just do a basic Taylor expansion if in the velocity, it turns out that you get this frictional force. So this total force F here is going to be linearly proportional to the velocity V with a negative coefficient, and that's friction. And that's how we're going to slow this atom down. And so intuitively, what's happening here is that the Doppler shift caused by the atom's motion is being canceled out by the detuning which we're applying to create this velocity-dependent radiation pressure force. Aha! So if this is just one atom moving in one direction with one laser beam, let's scale it up. And that's how you make a very basic laser trap. The schematic which I'm showing you here is what's called a magneto-optical trap. So the ingredients are on the left-hand side here. So what I'm showing you is a basic schematic of this trap. The black arrows correspond to counterpropagating laser beams in the X direction, the Y direction, and the Z direction to get cooling in the X, Y, and Z directions. I've also added some electromagnetic coils here. So coil here and a coil here. I'm not going to go into the details about this, but suffice to say, these electromagnets create a spatially dependent magnetic field. This spatially dependent magnetic field will create a spatially dependent Zeeman shift because these atoms have a magnetic moment. And the spatially dependent Zeeman shift will bring these laser beams in and out of resonance. So this is sort of by cartoon on this right-hand side. This is the Z position. These atoms will be magnetic, and so their energies will change depending upon their magnetic substate, which means that these lasers will come into resonance at different positions. And so what I've done is I've made a radiation pressure force which depends upon position. Well, that's what a trap is, right? A potential energy is just a position-dependent force. So I can go ahead and do this in the lab. So what I'm showing you here is just a cell phone picture of atoms inside this magneto-optical trap. And so this is all occurring inside a stainless steel vacuum chamber because I want to avoid any sort of background collisions with some sort of ambient gas. And so my trapped atoms are right here at the center of the trap. And what's happening is these atoms are absorbing photons from these 6 counterpropagating laser beams and then re-emitting them via spontaneous emission. And that spontaneous emission is what you're seeing with your eye because it's going off in all directions. And it's being captured in this case by this cell phone camera. You can go ahead and ignore this little guy over here. That's a lens flare. Okay, so zooming out a little bit, this is sort of what it looks like in the lab. So again, all of these experiments go inside a stainless steel vacuum chamber. And that's what I'm showing you over here. And again, you can see that there's this ball of atoms here that again are being trapped by this spatially dependent radiation pressure force. So these are actually lithium atoms, and this corresponds to a cold gas of lithium atoms around 3 billion in number and about 1 millikelvin. 1 millikelvin, that's pretty cold. So where does that come from? Well, it turns out that that temperature limit depends upon this parameter gamma here, which if you recall, is this uncertainty in the transition energy. And it turns out that it's limited by spontaneous emission. So this is already super cold, but how do I get even colder? So the way to do that, and which will be a theme for this entire talk, is with light. So far I've been discussing how what's called resonant phenomenon, which is to say that an atom is actually absorbing a photon and is going to live in this excited state. And it's going to re-emit it via spontaneous emission, which then creates this radiation pressure force, which we discussed. And as I mentioned, the scattering force is temperature limited by spontaneous emission. So the way that we can trap atoms and get even colder is with far detuned light. And it turns out that when you apply light that's far detuned, you get an additional trapping force. So the way that this works is that you have, again, say our two-level system, and we apply laser light that's far red detuned. That is to say that this detuning delta here is much, much greater than the transition line with capital gamma. And it turns out what this does is it creates what's called an induced dipole in the atom. So the way to think about this is that a laser beam, right, is an electromagnetic wave, which has an electric field. And this electric field can polarize, say, our atoms, right, because the positive charge on the inside of the atom will feel a differential force with respect to the negatively charged exterior. This creates a dipole on the atom. So it turns out if you do some math, this results in what's called a dipole force or a dipole potential, which I'm showing you here on the bottom. And the salient feature here is that this dipole potential depends upon, again, the intensity I and this detuning delta. So if I have a very intense beam, it'll feel a very large potential energy. And in the experiments that I'll be talking about today, we'll be considering deltas which are negative, that is to say, red detuned. So that means that atoms will be attracted to the regions of highest intensity, okay? So for those of you curious and taking your quantum courses, you can derive this potential for yourself. It comes from the AC Stark shift. For the biophysicists out there, it's related to a phenomenon known as optical tweezers, and it's also related to the physics of atomic polarizability. And what's neat about this particular trapping phenomenon is that there's effectively no temperature lower bound. And this is a consequence of the fact that this trapping mechanism doesn't fundamentally rely on spontaneous emission, right? This pressure force relied on the fact that atoms were going to be continually absorbing and re-emitting photons. But this is not happening here. There's no actual photon being absorbed. So let's go ahead and do this in the lab. So the way that we're going to do this experiment is I'm going to consider my, say, gas of atoms, say that magneto-optical trap that I was showing you before. So here we have this background gas, and we're going to shine on this very far red detuned laser beam over here. Okay, and as I mentioned, the atoms will be attracted to the regions of highest intensity given by this dipole potential. So that means that the atoms will coalesce at this point here because I'm focusing down this laser beam to get a really high intensity. And we can go ahead and just do this in the lab, and we see the following. So what you're looking at over here on the right-hand side is actual data that we take in the lab. This yellow ball corresponds to an image of trapped lithium atoms. You can go ahead and ignore this little X here. And so what we're doing is we're shining in an intense laser beam, beam 1, along this direction, and another laser beam of high intensity, beam 2, along this direction. And at their intersection is the point of maximum intensity. And as I mentioned before, that's where these atoms are going to attract, and that's that trapping potential there. And so this corresponds to about 12 million atoms at about 2 microkelvin. So that's far less in number and temperature than the previous trap for the reasons that I just mentioned. And so that's fantastic. This is quite cold. And since I have just shown you data that's actually that we take in the lab, we don't take data with cell phone cameras. I'm just going to take a quick aside and talk to you about how we take data in a cold atom lab. And as you can probably guess, the answer is with light. So that's what I'm showing you here. So here is a gas of, say, atoms, which is this blue ball. It's a cartoon. And what I'm going to do is I'm going to shine light that's resonant with that transition. And as we just mentioned, the atoms are going to absorb those photons via stimulated emission, stimulated absorption. And so what we can do is through some application of just some lenses, we can image this shadow onto a camera. And this involves, some basic ray optics. It's that topic that you learned in lower division physics that you probably forgot very quickly because you're like, I'm never going to use it. It turns out that it's super useful in atomic, molecular, and optical physics. Okay, so what we do is we'll take a series of images. So here's the first image. This is the image of the atoms as they're casting the shadow. So IF corresponds to intensity final, so that's with the atoms. So you can see here this blackness corresponds to the shadow that these atoms are casting on our camera. I'll then take another picture with the light only for a reference. And then finally, I'll take a dark image. And what I'm going to do then is I'm going to combine these three images to construct what's called an optical density, which we call OD. And that just relates these two intensities, IF and II. So, and this is what I was just showing you before in the previous slide, which is this optical density. So what does this picture tell us? Well, it tells us another thing, number of things. The magnitude of the shadow tells us the number of atoms there, right? So the magnitude of the optical density. Furthermore, well, this is a picture, right? So it tells me the spatial distribution of the atoms. It turns out that I can also measure the momentum of these atoms. I can also say measure the energy of these atoms. And I can also say measure the magnetic state of these atoms. And so this very relatively simple imaging technique tells us really a number of important aspects of our atomic cloud. So I'm going to go ahead and demonstrate the power of this technique through an example measurement. And this example is pretty important because so far I've been telling you a lot about temperatures and stuff. Well, how do I measure temperature in the lab? And this works in the following way. So consider that dipole trap that I was just showing you a few slides ago. What I can just do in the lab is I can take my laser beams and then turn them off. So what are the atoms going to do? Well, they have some sort of finite temperature, and with no potential, their energy is just p squared over 2m. So that means by statistical mechanics, they're going to expand ballistically. And what I can do is I can just take a series of images of the atomic cloud as it's undergoing this ballistic expansion. So this is at 0.5 milliseconds time of flight. I can then image it at, say, 2 milliseconds, 3 milliseconds, and 6 milliseconds. Well, what am I doing here? Well, this is just basically a rudimentary movie, right? A movie is just a series of still images taken sequentially in time. And that's exactly what I'm doing here. And so you can make cute little movies of the atoms expanding as I release them from this trap. Okay, so that's fantastic. And so what I can do is it turns out that the most pertinent way to describe this is through a Gaussian fit. So if I plot, say, the time of flight, this flight time, versus the Gaussian radius, I'm able to extract, say, the temperature, the initial size of the atomic cloud, and also the number of atoms. And so when I quote atom numbers and temperatures, in the back of your mind, you should be thinking about this plot. Fantastic. And so now I'm going to sort of just briefly summarize all these laser cooling techniques in the following slide. So this is actually what an experimental sequence would look like in the lab. So there's a lot of things going on here, but I just want to point out that, as I mentioned before, we start off by heating our atomic metals. So in this case, they are initially at 550 degrees centigrade. And through all these laser cooling steps, they get colder and colder and colder and colder. And also the number of atoms decreases. So initially I had like 1 billion atoms, and at the end of the day, I'm only going to have a few 100,000. So I'm not really going to go into the physics of all these steps, although you should recognize this magneto-optical trap and this optical dipole trap that I mentioned previously. But you already know all the basic ingredients for how this physics works. These top sections rely on laser cooling using near detuned light, i.e. they're going to use that radiation pressure force. And on the bottom section, these are traps going to be made of far detuned light. So that means that there's no radiation pressure force, so I can get much, much colder. What I also want to point out on this slide is that these experimental steps take a variety of timescales. So some are long, like 15 seconds, and some are short. So if you add up all these numbers, you wind up with around 30 seconds. So that means is because the universe has given us atoms and they're all identical, what I'm going to be doing is I'm going to be making a gas of ultracold atoms every 30 seconds. So you can imagine 30 seconds go by, I cool all these atoms, I do some measurements and I throw them away. And the next 30 seconds, I get another identical batch of atoms, right? Because all the atoms are identical. And that's one of the great things about this field is that I can create a relatively identical sample across many, many iterations of our experiment. So it takes 30 seconds. So you're really just limited by your patience, or more accurately, the patience of your graduate students working in your lab. Great. So once I have all these atoms and I cool them down to a very cold temperature, what happens to them? Well, this is what's going to be the formation of what's this called a Bose-Einstein condensate in the case of composite bosons. So from your class, you should probably be aware, right, that atoms or all, massive particles have wavelengths associated with them given by their de Broglie wavelength. And so at very high temperatures, this wavelength is very short, lambda equals h over p. So they're basically going to behave like these little billiard balls. But as I cool them down, their de Broglie wavelength is going to get longer and longer. And in the case of bosons, as these wave functions begin to overlap, they're going to constructively interfere until eventually, beyond some sort of critical temperature, Tc here, and going down to T equals 0, you're going to get this giant matter wave overlap. And this is this Bose-Einstein condensate where all the atoms, all their wave functions constructively interfered and sum up to make this BEC. And so we can see this in the lab in the following way. So on the left-hand side, in this top left area, I'm showing you data which is very similar to what I was showing you before, right? I'm going to take my atoms and trap. I'm going to let them expand in time of flight, so I'm able to infer something about their temperature. So going left to right, I'm decreasing the temperature. And so initially, at these quote-unquote hotter temperatures, the distribution is rather smushed out. It's Gaussian in nature. This is a thermal distribution. But as I get colder and colder, you can see the appearance of this sort of hard core in the center until all the atoms are only in this hard core. And that's this BEC. So initially, there's only thermal atoms. That's around over here. Then some of them are in this Bose-Einstein condensate. And eventually, all of them are in this single phase of matter. And this is a thermal phase transition. And so that data that I was showing you on the title slide is just a 3D rendering of this data here. So we can also say measure the number of atoms in this condensate here on the y-axis versus say the temperature. And we can see this classic curve of this phase transition as the atoms get closer and closer to temperature 0. You can never actually equals T equals 0, but they're going to be very cold around, say, less than 50 nanokelvin. Fantastic. So I also mentioned that I worked with other sorts of atoms. This is a Bose-Einstein condensate of lithium. I also work with other atoms. I work with rubidium, which is a composite boson, and potassium-40, which is a composite fermion, and those will make a Bose-Einstein condensate and a degenerate Fermi gas, respectively. Okay? And I'm not going to talk about these too much. So the story so far, this sort of whirlwind story, is that I can use light, namely lasers, to trap and cool these gases down to cold temperatures. And I can then use these techniques to create quantum degenerate matter, where I'm really starting to see the many-body quantum behavior of these materials. And furthermore, I didn't really mention this, I didn't go into detail about this in this talk, but it turns out that using the tools of atomic physics, we have a control over a variety of microscopic as well as macroscopic properties of these atomic gases. So I already mentioned that we can control the temperature. It turns out that we also can, say, control the interactions. And as you already know, we can tune, say, the potential energy that these things see. So what I'm trying to tell you here is that we really have exquisite control over these atomic gases. So with all this awesome control, how can we use it? And so the answer is with this concept of quantum simulation. And I think this is best explained through the analogy that I'm showing you on this slide, which is an analogy between the field of condensed matter physics and atomic physics. So for those of you unfamiliar, condensed matter physics deals with the physics of materials, right? And so in this case, we're going to be considering, say, electrons hopping around in ionic lattices. And there are a variety of really important physical problems that we're trying to solve in this field as the community. So for example, say you want to understand how graphene works, or say you want to understand high temperature superconductivity, or say you want to understand how topological insulators work. These are a variety of outstanding, really important problems. But studying these sorts of systems can be challenging for a variety of reasons. Namely, these occur, say, at large energies and densities, right? The lattice spacing in a typical material is going to be on the order of an angstrom, or say around, a fraction of a nanometer. So you can only image that with, say, like an AFM or something. Furthermore, the interactions in these systems are in general quite complicated, right? There's going to be electron-electron collisions. There's going to be defects in your material. There's going to be electrons scattering off of phonons, all sorts of complicated things. And moreover, the parameters in the system are fixed, right? You can't change the fine structure, at least as far as I know. And you can't, say, tune the Coulomb repulsion between two electrons or attraction between an electron and a proton, right? That's just not physical. And so what we can do as atomic physicists is we can bring a complementary perspective to be able to understand and analyze these sorts of very fundamental problems in condensed matter physics. And so what we do is, instead of considering, say, electrons in ionic lattices, we consider cold atoms hopping around in optical lattices. These are these potential energies which are going to be created with light. And instead of actually making these physical materials in a fabrication room, we're going to simulate these problems. And what I mean by that is, say you have some sort of Hamiltonian which governs the properties of your material. I can just tune down all the coupling coefficients by, say, a factor of 10. And because physics is scalable, I'll be able to realize the same fundamental properties of these condensed matter systems. And what's great about these atomic physics systems is that they're much more experimentally tenable to deal with. So, for example, they're going to occur at many orders of magnitude lower densities and energies. And this is because our lattices, our periodic potentials, are made of light. So they occur sort of at distance scales of order of micron. Furthermore, as I just mentioned, we can, say, control the interactions between atoms, right, which is something you can never do in a real material. And furthermore, we can, say, tune the parameters in our system at will, right? I can just take my laser and I can just tune a knob and I can tune the power down, right? You could never do that in a real material. And so what I'm showing you here, again, is an image of potassium atoms in one of these optical lattices. And so what I'm trying to say is that there's an analogy between atoms in this system and, say, electrons in this system. Okay, so that's the idea of quantum simulation. And in particular, I'm particularly interested in transport phenomenon, which is to say, you have electrons that are going to be moving around in a lattice. I'm going to be interested in how the dynamics of these atomic gases in these optical lattice systems. And so I'm going to show you a variety of experiments which shows you how quantum simulation works. And also I'm going to show you how cold atoms can also go beyond what is even hypothetically realizable in a condensed matter lab. Great. So to do that, first I need to tell you, well, how does an optical lattice work? And it's actually quite straightforward. So here's that dipole trap that I was showing you before, right? Where I have this intense laser beam and the atoms are going to be trapped over here. And so to make an optical lattice, all I have to do is put a little mirror on one end, boop, right over here. And what this does is it's going to retroreflect the laser beam. Well, as we just discussed, a laser beam is an electromagnetic wave. So if I have two waves going in the opposite direction, that's going to make a standing wave. So if I time average the standing wave to look at the expectation value, say, of the intensity, I get a periodic tiling in intensity. Aha, this periodic tiling in intensity is therefore a periodic tiling in potential energy, right? Because this intensity is related to this dipole potential. So I have a periodic potential energy. Hey, that's a lattice. And so what I'm saying is that there's an analogy here between electrons hopping around in a Coulomb-like lattice and atoms hopping around in this lattice made of light. And what's great about this optical lattice is that it's virtually perfect. The coherence length of lasers is very long. So for all intents and purposes, there are going to be absolutely zero defects in the system. Great. And so with this power, we're going to talk about some experiments. But first, I just want to mention how we can think about the states in this lattice, right? So this is quantum mechanics, right? So they can be described via some eigenstates. So let's say consider this simple 1D optical lattice. It's going to have a single particle Hamiltonian given by the following, right? It's just a kinetic energy term with some potential energy term. And it turns out that the energy will be parameterized by what's called the recoil energy. It's a natural energy in these sorts of systems, and which is also described by the lattice light that I'm applying. So for those of you who have taken solid state physics, it turns out that this system is best described what are called Bloch bands. So for those of you unfamiliar, there's a couple of features which are important. So on the y-axis here is the energy, and on the x-axis is momentum. In this case, it's called quasi-momentum because I've broken continuous spatial translational symmetry in exchange for discrete translational symmetry. And so these colors correspond to different energies that the atoms can have in this lattice. So there's this ground band, which is the blue. There's this second band, which is this red. And then there's a third band, a fourth band, a fifth band, et cetera, et cetera. And so you can think about this as analogous to how, like in free space, energy equals p squared over 2m, right? Except now I'm using quasi-momentum instead of p. So experimentally, what I'm going to do is I'm going to take these atoms, in this case, this Bose-Einstein condensate, and I'm going to initialize it in one of the eigenstates of the optical lattice. That is to say, I'm going to put it in this ground band at the center of this quasi-momentum distribution here, because it's initially going to be at rest, so it'll have no momentum. Great. So now I want to consider a couple of transport experiments. So I think one of the most basic transport experiments you can think about is, say I have particles in a lattice. What happens when I apply a constant force to particles in a lattice? And the answer is Bloch oscillations. So what are Bloch oscillations? Bloch oscillations are these characteristic oscillations in quasi-momentum, which is characterized by what's called Bragg scattering at the zone edge. Okay, so that's a bunch of words. What's going to happen is that from a cartoon perspective, atoms are going to start off at the center here. Their momentum is then going to evolve with this force I'm applying, right? F equals dpdt. And it's going to reach the edge here. And it turns out what's going to happen is it scatters against some of these lattice phonons and then continues along its merry way like this. And so this is going to create a characteristic sawtooth evolution in the quasi-momentum. And we can go ahead and do this in the lab. So what I'm showing you here on the bottom left is the experiment which I just mentioned, where we apply a force and we look at the quasi-momentum. And you can see this characteristic sawtooth evolution in the quasi-momentum. So this, maybe this is a little bit challenging to look at, but you can imagine that this is a slice. So this sort of rectangle here is one image, and then I wait for another period of time and I take another image, and it's just a composite image of many realizations, okay? So in this case, the force is going to be dependent upon the Bloch, this frequency of oscillation called the Bloch frequency FB, depends upon the local force. And for technical reasons, I'll be applying the force via a magnetic field gradient. So it turns out that this notion of Bloch oscillations has been well understood for many decades, but it turns out it's quite challenging to observe in a condensed matter lab. In fact, you can really only do it with applying what's called a superlattice. And the reason for this is what I mentioned before about electron-electron collisions, defects, and so it's really hard to see. But what's even harder to see is that not only are there oscillations in quasi-momentum, but there are also oscillations in position space. And these are called position space oscillations. And while this would be virtually impossible to see in a condensed matter lab, we are able to see it quite easily in our optical lattice. So the way to understand position space Bloch oscillations requires a bit of a background. So it depends upon what's called a Bose-Hubbard Hamiltonian. So if you've never seen this before, that's okay. The important part is that it depends upon this tunneling rate J, a interaction energy U, and an applied force F. So as I mentioned before, the atoms are going to evolve in quasi-momentum with the force. And it turns out that they're going to undergo a spatial oscillation given by their group velocity. And in this case, the oscillation amplitude is given by what's called this Wannier-Stark localization length, which depends upon the tunneling rate and the local applied force. And as I mentioned, these are traditionally challenging to measure in a condensed matter lab. But what's great about optical lattices, or cold atoms and optical lattices, is I can just get rid of all interactions. Great, don't have to worry about this term, awesome. And I can also say, tune this tunneling rate to be very high and also apply a very low force. And so we can just go ahead and see this in this lab. So these are these position space Bloch oscillations. Again, this is a composite image. Here, time is on the x-axis and position is on the y-axis. And we can say, integrate our data over here, and we get an excellent agreement with theoretical predictions. And so this got us a nice shout out from the editors at PRL. So Adams put on a Bloch party. And so I like to imagine that Zener and Bloch are having a party and they have little party hats on. Fantastic. So not only were we able to see this, but we can also verify a bunch of quantitative features about these sorts of oscillations. So here we can say compare the amplitude of these oscillations versus the applied force expressed in units of the Bloch frequency. And we can see excellent agreement between the data and fit parameter free theory. We can also say the tunneling rate versus the amplitude. And so we really think we understand what's going on with these position space Bloch oscillations. Moreover, we can say unify the existing oscillations in quasi-momentum with those in position. And the way that we can do that is via that time of flight measurement that I was just telling you about, right? So what I will do is I'll have these position space Bloch oscillations. Again, this is a composite image, time on the x-axis, position on the y-axis. And for each of these moments in time, I'll then perform that time of flight measurement, right? So if I take these atoms, they oscillate in position, and then I let them go, they're going to expand ballistically. And so position equals velocity times time. So they're going to linearly expand with the time of flight. That allows me to then extract a simultaneous mapping of not only the position evolution, but also the momentum evolution, which then allows me to reconstruct the entire phase space time evolution of a Bloch oscillation. So this is kind of a complicated plot. What's happening here is on the x-axis is position, and on the y-axis is momentum, parameterized in terms of this whole time. And so atoms will start off over here, and they'll begin to Bloch oscillate before they Bragg scatter and continue on their merry way. And so with this measurement, we were able to unify and provide a complete perspective on what happens during Bloch oscillations, which I think is really great. I guess I'm running short on time, but I also want to show you how we can go beyond what's traditionally realizable in a condensed matter lab, right? You could still see Bloch or quasi-momentum oscillations in a condensed matter lab. Now I want to show you something which would be basically impossible. So what I'm going to do is I'm going to enhance the transport by modulating my optical lattice. So here is that familiar 1D Hamiltonian. And what I'm going to do is I'm going to modulate the amplitude of this lattice with some frequency omega. And from a cartoon perspective, this is going to create these virtual photons, which is going to say connect, say, this third band with my ground band. So what's going to happen? So first, these are the traditional position space Bloch oscillations that I was just showing you before, where it's oscillating, okay? And then I'm going to turn on the modulation. And so what you're seeing here is actually quite remarkable. The atoms begin to have some sort of localized behavior from this position space Bloch oscillations, but then they rocket across our trap here over 2,000 lattice sites, which is about 1 millimeter. And 1 millimeter might not sound big to you, but remember, this is a Bose-Einstein condensate, which is quite small, actually. So the way that you can understand this is that this perturbation is connecting these two different eigenstates, and through, say, time-dependent perturbation theory, you'll get some new eigenstates which commute with your time-dependent Hamiltonian. And your new states will have some excited band character and some ground band character, and conversely, some excited band character and ground band character at the center. So what you're seeing here is some sort of hybrid motion where sometimes it exhibits some ground band character, and other times it exhibits excited band character, which will greatly enhance its transport properties. We can then say, compare these oscillations with fit parameter free theory. We can say vary the frequency or vary the force, and we see excellent agreement between our data and theoretical predictions. So again, we understand what's going on. Moreover, I could say dynamically control the modulation. I can turn it on or off. So here is no modulation. These are these position space Bloch oscillations. I can then say turn on the modulation and then turn it off, and the atoms are transported across. Or I could say turn it on, let them come across and come back, and then turn it off. So this allows us an exquisite degree of control using these optical lattices. Moreover, I could say even hybridize even higher excited states. So this is that 1,3 hybridization that I was just referring to. We could even say connect to even higher excited states and even get faster transport. In this case, what's actually happening is this BEC is being ripped asunder, which I think is quite amazing. And those are just a couple of experiments that we can do with transport. So now I'm going to sort of, with the last time I'm going to have, I'm going to sort of conclude with a little bit of what I've been working on more recently, which is at the University of Toronto, where we measure AC conductivity in an optical lattice. So the setup is relatively similar. Again, as I mentioned, we're going to have these atoms in this optical lattice, and we're going to apply a periodic force on them. And what this allows us to do is, say, extract the conductivity of these systems. And so what I'll do is I'll measure the displacement to a periodic forcing that allows us to get the conductivity here by looking at the displacement of the atomic cloud. And by comparing the force that I'm applying, which is this dash curve, to the displacement, which is this blue curve, I'm able to reconstruct sort of an Ohm's law, which relates the current of the atoms to the force that I'm applying. And that allows me to get, say, a real conductivity and an imaginary part of the conductivity. And then I can study things, I can study things such as, say, the conductivity as a function of the applied lattice. And so I'm not really going to go into this. And I think I'll go ahead and just summarize what I've told you about so far, at least in the science portion of this talk. So I hope I've convinced you through a variety of examples that light, in particular lasers, are an amazing, powerful tool for trapping and cooling atomic gases. Moreover, that these atomic gases can provide a really rich playground for creating and understanding quantum matter, this many-body quantum states. And furthermore, I've shown you a variety of experiments where we can use these cold atoms in optical lattices to realize a variety of really interesting and neat transport phenomena. So with that, I'd like to go ahead and acknowledge my group at Santa Barbara, as well as the group at the University of Toronto, where I am now. I think this being this seminar, I'm just going to go ahead and sort of give you a flavor. Am I okay on time? I don't know how long we're supposed to be going.
Yeah, you
can
go on a little longer. Yeah.
So I'm going to give you an idea of what it's like to work in an AMO lab, and then I'll conclude with a couple of comments about sort of my own personal academic journey. So this is the experiment at UCSB. So this is what's called an optical table, if you're not familiar. There's a stainless steel vacuum chamber. There's a bunch of lasers going on. Usually we like to think about these kinds of experiments as being the most complicated experiments that you can have on a tabletop. And then here, so actually for my PhD, for grad school, I joined a very young group. And so this is actually the lab as it looked like in 2012. And I spent the majority of my grad school building these sorts of machines. So this is what they sort of look like in the beginning phases. So see this little light glowy area? That's where this is now. So this was a lot of fun, a lot of work, but that's sort of what I sort of signed up for in grad school. This, as I mentioned, this includes a lot of laser beams. So these blue guys over here are a variety of lasers, which we're going to be using to generate that cooling light and those optical lattices that I mentioned. And nowadays, I'm at the University of Toronto. So if you come by the city, whenever travel is allowed again, we're right over here. And also, in a similar sense, these experiments are quite complicated, and they have lots of, say, mirrors and wave plates for controlling the states of these lights. And this is the stainless steel vacuum chamber where we trap atoms at University of Toronto. This is a cute picture of what lasers look like in the lab. You know, I think from a cartoon perspective, everyone thinks about lasers as being able to see them, but of course you can't see them with your rear eye because otherwise they'd be scattering lots of light, and that would be bad. So now I just want to maybe talk a little bit about my own personal journey in academia. As Alex mentioned at the beginning of this talk, I did my undergraduate at UC Berkeley. And what I was working on then was I was working on a database for UV detector research. So actually my background as an undergrad was very much related to astrophysics. And I didn't really like what I did in undergrad. No one really used what I was making. I was making this database. I was also working by myself basically all the time. And so I think everyone's functions a little bit differently, but for me personally, It was rather hard to stay focused working by myself. Also, I didn't realize that I had to do a lot of coding. And I like coding, but I don't like doing it all the time, it turns out. But one of the things I did like was designing things. I thought building something was really awesome, because once you build something, nobody can ever take that away from you, right? And so then for graduate school at UCSB, I sort of took that information and I kind of switched fields. So I went from this sort of detector-based research to atomic, molecular, and optical physics. And so this is just sort of a random collection of bullet points to remind myself of things to mention. But I was able to work on building a lab from the ground up. I wanted some sort of experience of getting hands-on work. This meant that I had to work in a very closely knit team with a group of graduate students. And that was a really valuable experience because I was able to make a lot of great friends and keep myself motivated. It also meant that I got to work with my hands every day. As I mentioned before, I don't like coding all the time. Especially nowadays, I really am anxious when I'm not in lab. There's something very satisfying about hammering something or building something. But at the same time, if you work in a field such as AMO, because atoms are such ideal systems, they're very clean. So in fact, most of the theory work is pretty accessible to experimentalists. So I think in that work that I was showing you previously, basically all that theory we did in-house. There are certain things that we have to talk to theorists about to collaborate, but for the most part, a lot of what we do, we're able to do on our own. Also, lasers are awesome. It's fun to get to work with really expensive equipment as an experimentalist. You also get tons of hands-on skills like electronics, optics. Surprisingly, I have to work a lot with water because we have to water cool our electromagnets. You get to work with UHV systems, ultra high vacuum systems. I suppose as an experimentalist, you have to be prepared to break things. So I think during graduate school, I probably broke many thousands of dollars worth of equipment, which was terrifying at first, but is really a rewarding experience. I think something else that I took from undergrad was that I wanted constant feedback. So I intentionally worked with a relatively young professor because he didn't have tenure. So that meant that there's going to be lots of feedback and he'd have a very strong interest in my own personal success. But that also meant that I had a relatively long PhD, so about 7 years. And one of the also things that I sort of liked about working in this sort of field, or building a lab, was it really sort of forced me to learn how to talk to a variety of people. I had to learn how to talk to vendors, different colleagues, companies, and things like that. I should also point out that I also thought about going into CMX for a while. And so nowadays I'm doing a postdoc in Toronto. So just sort of briefly, I'll just mention some of my thoughts on that. When I graduated from grad school, I knew that I liked the research, but I was kind of unsure about what I wanted to do in life. So I decided I would postpone going into the private sector because I think research is fun. You get to play around with stuff and you get to, follow your own nose about what you want to investigate. Furthermore, there's also sort of a two-body aspect to it. My significant other is also doing a postdoc in Montreal. So especially now, given the sort of health situation with the border, that's been a real boon. And something else that I thought about was that I wanted to work with a more well-established professor. And as Alex also mentioned at the beginning of this talk, I grew up in Southern California. I went to Berkeley and then went to Santa Barbara. And so I wanted an experience to leave California, although it's too cold here. So I think I'll just sort of give some more other unsolicited opinions, if that's okay. So if I had to give any sort of tips to aspiring undergrads who want to go into a PhD in physics, one of the first things I'd say is don't be afraid to change fields or advisors. You all here are really smart, and I'm sure you'll find many things interesting and amazing to work on. I know that basically whenever I hear someone give a talk, I'm like, oh, that's so awesome. I wish I could do that. But you don't really have the time to do all those things. Also, grad school is really long. I was in grad school for 7 years. So I would definitely advise you to make your choices to maximize your happiness. It's 7 years is a long time to be unhappy in school. Also, your relationship with your PI is probably the most important factor in your education. If you don't get along with them, that's going to cause a lot of issues for your career. So I really like to emphasize that you should have a good relationship with them, or at least They like you and you tolerate them at a minimum, I'd say. Also, I'm not so sure if this is true for all fields, but at least in my opinion, you should learn people and networking skills. I got into STEM and physics because I didn't like people, a little bit of an introvert, but that's just not possible in this sort of modern world. It's really important to learn how to interact with people and to network. Also, don't go to grad school for the money. There's a lot of other ways to make money. Yeah. And also, I just want to emphasize that imposter syndrome is a really real phenomenon, especially if you're in a minority group. So I really encourage you to find friends and share experiences and support each other. And so my very, very last slide, thank you for bearing with me here, is I just want to share a little bit about my perspectives as a member of the LGBT community. And so forgive me for just sort of reading off these bullet points, but academia is relatively progressive. But you might have heard in the news, physics sort of has a bad historical reputation, and that's just sort of the reality of the world that we live in at this moment. But for the most part, you'll be able to find peers and colleagues who are very supportive. And so I, in fact, chose my PI because I felt like he would be more respectful. So I encourage you, if this is a concern for you, to make sure to not only have your PI interview you, but you should also be interviewing your PI. Again, I can't emphasize enough that it's really important to find a support group, peers and friends who will support you throughout your education. Again, grad school's a marathon. From a personal perspective about being trans, it's actually kind of tough. We can talk more about this perhaps in a question section, but having to need to reset professional relationship was very frustrating. You know, I had to contact vendors, had to meet new colleagues at conferences, and you know, also getting my name changed on journal articles was really frustrating. And I would definitely encourage you to choose progressive areas to live. And one of the other things I like to point out that's sort of challenging as a trans person is that, you know, you have to take some medical leave of absences because you have sort of different medical needs. And that's stressful. And the only thing I can really say is that it's important to find a community, namely your professor, who is very supportive, and you feel like that won't be an issue with them. And I think that was really important that I had chose a PI who I felt like I could work with very well. And so with that, I'd like to thank you for your attention and open it up to any questions.
Great talk. Thank you so much, Cora, for that excellent talk and for sharing all of that with us. So if anyone in the audience would like to ask a question, you can type it into the Q&A. I'll also add, Cora was kind enough to volunteer to stick around after her talk. It'll be in a separate Zoom link to talk to any students who are more interested in speaking with her about her research, about Berkeley, about Santa Barbara, about whatever they like in a more informal setting. So if you're interested in joining for that, please send me, not in the Q&A, but in a chat, a message, and I can share the link for that with you. But first, are there any just sort of general questions about the talk that anyone has? So we have a first question. I don't know, Cora, if you can see that. It says, at what wavelength are you using to slow down the atom, and how does one go by determining the specific wavelength?
Yeah, so that's a great question. That's sort of a technical detail I didn't go into. Hopefully you guys can see my screen again. So the properties of atoms are sort of given to us by the universe. You know, I had mentioned that atoms are sort of this sort of quasi two-level system, but it turns out, you know, they have many different sort of energy levels. That's what I'm showing you here. And so the transitions that we deal with are given to us by the atom. So in this case, for lithium, it corresponds to 671 nanometers, which is sort of this red wavelength that you could see by eye. But conversely, for say potassium 40, that wavelength is actually at 767 nanometers, which is basically at the edge of the human sight. So that's sort of how we choose the wavelength.
All right, Thank you, Armando, for that question. So next we have a sort of anonymous question. How did you probe whether your PI would be respectful or not?
That's a great question. So I didn't really do this so much for grad school. Yeah, it's kind of hard to get a very specific answer. I think one of the most important things is when you're going to grad school, you're going to hopefully be able to visit them and meet them in person. And those sort of in-person interactions, I think, will really give you a feel for who that person is. I also totally recommend that when you go choose a PI, you not only talk to them, but you also talk to their colleagues, not really their colleagues, but their students, because their grad students will sort of really give you a candid perspective on who they are as a person. I certainly didn't have the confidence to sort of be upfront and ask that sort of question when I was applying for grad school. But when I was applying for postdocs, this is something that was really at the forefront of my sort of decision making. And so when I was interviewing with groups to work with for a postdoc, after talking about science, one of the things I asked with was, how do you feel about women in physics or LGBT things? Like, are you aware of? I think the way I phrased it was like, what sorts of programs are you aware of here, right? And so basically, most universities will have these sorts of things. So if they didn't have any idea what was going on, then it was clear that they, maybe they were respectful, but maybe they weren't super into it. But for people who, had an answer right away, it was clear that it's something that they had thought about. So maybe it's kind of hard to say exactly, but hopefully that gives you an idea of some tips that you can use.
Great. Thank you so much. And thank you for that question. All right, so we have a question from Eric. Are there nuclear applications like understanding fusion reactions or structure for your work or related to your work?
Yeah, that's a good question. So that sort of question sort of gets at the energy scales of this sort of system. And I guess to preface this, the short answer is no. And the reason for this is that so the energies that I'm considering here are extremely low. These are like nanokelvin energy scale. So these are the kinetic energies of the atoms. And you can imagine that if I wanted to access the nuclear degrees of freedom of these atoms, I would need to be able to, I would have to put in energy to unlock like the strong or weak forces inside the nucleus. And these energy scales are just so far fewer. And in fact, we use this in the lab because usually when you think about fermions and bosons, you think about like electrons or protons or photons, right? Or like the Higgs boson or something. These are not fundamental particles, right? These are atoms. They're composed of subatomic particles. And so what we do is by working at these very low energies, we basically freeze out the nuclear degrees of freedom, which allows us to consider these atoms not as being composed of many things, but as being what I called composite fermions or composite bosons, where the total spin is given by the sum of the nuclear part and the electron part.
Great, thank you. And thank you for that question, Eric. Are there any, I know I kept you guys, we went a little 5 minutes over, but are there any final questions before we let our speaker go? All right. Well, if not, thank you so much, Cora. Thank you everyone for coming. We'll have our next talk in 2 weeks. So be sure to pay attention for that email or check. We always update our calendar that you can go to through the CalBridge website to see our future talks. So thank you so much, everyone. And thank you, Cora.
Thank you for having me. Bye.
So I think we're done.
Yeah.